A spherical snowball is melting at a rate proportional to its surface area. At what rate is the radius of the snowball changing in time? So before we tackle this problem, let's think a little bit about the problem statement. So the claim is that the snowball is melting at a rate proportional to its surface area. So we have some sort of spherical snowball that looks like that. So that's supposed to be a sphere, approximately. And it's melting at a rate proportional to its surface area. So why would that be the case? Well, the surface area basically is a measure of the contact between the ice and the outside conditions. So the larger the surface area, the more heat transfer there's going to be between the snowball and its surroundings. So it's a pretty good approximation or model to say that the rate of change of the snowball is proportional to its surface area. You see the same sort of thing in a raindrop. The raindrop would be evaporating at the rate of change proportional to the surface area, because the surface area basically controls how much interaction there can be between the sphere and the outside conditions. So melting at a rate, so what does this mean? So we have to read a little bit into the problem. So it probably has something to do with the change of the volume. So at what rate is the volume increasing or decreasing? So dV dt is going to equal K times S. So V is the volume, and then S is the surface area. And then since it's melting at a rate proportional to the surface area, we need a constant. So K is the constant of proportionality. And then we want to think a little bit about the sign, because we have a derivative and we want to think it should be positive or negative. Well, it's melting, so the volume should be decreasing, so the derivative should be negative. So that we don't have to deal with negative constants, let's make this minus Ks. That way we guarantee that K is going to be some positive number, because with a positive value of K, a positive surface area, dV dt will be negative. So it's melting at a rate, its volume is decreasing at a rate proportional to the surface area. And then we're asked to find basically what dr dt is. So dr dt is equal to what? So in order to do this, we're going to need to pull back the problem in terms of the variable r. So we want to describe everything using the variable r. Now luckily we have some basic equations from geometry that will let us do that. In particular, when we have a sphere, the volume is given by 1/3 pi r cubed. And the surface area, I'm just joking, 4/3 pi r cubed. The surface area is 4 pi r squared. So the volume is 4/3 pi r cubed, and the surface area is 4 pi r squared. So we can use the surface area formula to rephrase this as dV dt is equal to minus K 4 pi r squared. The rate of change of the snowball's volume is equal to some constant times, so negative K times 4 pi r squared. 4 pi r squared, remember, is just the surface area S. So it's still not saying anything differently. It's melting at a rate, in other words, the volume is changing at a rate proportional to the surface area. Now the related rates comes in because we have to, so this relates dV dt with r, but we don't know, we're not given the value of dV dt, but we have a second formula, the volume equation, that relates the volume to the radius again. So from the information given in the problem, in other words, from the physical model of the problem, we have this relationship, that the rate of change of the volume should be proportional to the surface area. So this is our physical assumption. Right, so this is in the problem statement. Second, we have the relationship between volume and radius, and this is given to us by geometry. So, and actually even replacing S with 4 pi r squared is another geometric relation that we use. But here we can use this relationship plus calculus to come up with an alternate expression for dV dt. So regardless of what our physical assumption is, whether volume is changing at a rate proportional to the surface area, or volume is changing at a constant rate, or volume is changing at a rate proportional to the surface area squared, dV dt and dr dt must be linked via the derivative of this equation. So from this equation, we're going to take its derivative. The derivative with respect to time is dV dt, So remember, with related rates, everything is implicitly a function of time. Derivative of v is going to be dv dt. Derivative of r is dr dt. Derivative of r cubed is the same as the derivative of r of t cubed. So it's 3 r of t squared times the derivative of the inside dr dt. So basically the 3 comes down, so dv dt, 3 comes down, we get 4 pi r squared times the derivative of the inside, which is dr dt. So this relationship has to hold for any sphere because it just is the derivative of the volume equation. So regardless of what the problem tells you about dv dt, any sphere changing in size has this relationship that dv dt is going to equal 4 pi r squared dr dt. So this is a kind of a general consequence of geometry. So let's use this formulation of dv dt in our physical assumption that says the rate of change of the volume is proportional to the surface area. Well, these two together, dv dt is just 4 pi r squared dr dt, and then negative ks is negative k times 4 pi r squared. Now you'll notice that a 4 pi r squared cancels on both sides, like this, which leaves us with just dr dt is equal to minus k. So basically, whenever you have a sphere such that the volume is changing at a rate proportional to the surface area, a consequence of that is that the radius has to be changing at a constant rate with respect to time. So the radius is just at a constant rate decreasing. Right? It's not going to be accelerating, it's not going to be moving faster than slower, it's going to decrease, the radius will decrease at a constant rate. So without doing calculus, which is really simple steps, v, derivative of v is dv dt, derivative of r cubed is 3 r squared dr dt, and boom, there you have it. Whenever you have this connection that the rate of change of the volume is proportional to the surface area, the mathematical consequence of that statement is that the radius must be changing at a constant rate. Moreover, the rate of change of the radius is exactly equal to this constant of proportionality. So the constant of proportionality that links the rate of change of volume to the surface area literally has the physical interpretation of being that's the rate at which the radius is changing in time. The units also make sense, so a quick reality check on this. The units of dv dt are going to be meters cubed per second. The units of s are going to be meters squared because it's surface area. So therefore the units of k must be meters per second, which jive with dr dt, right? Rate of change of length per unit time. So that checks out, and the answer is that dr dt is just equal to minus k, where k was that constant of proportionality.